Welcome back to The Explainer. Today, we're diving headfirst into a fascinating technical mystery that is, quite frankly, quietly wreaking havoc on production apps right now. Look, if you're building AI agents, writing tool calls, or just asking a language model to give you some structured JSON, you've probably designed what looks like a perfectly valid schema. But underneath that perfection, there's a hidden trap. A trap that's causing seemingly flawless JSON schemas to just silently crash the second they hit production.
Okay, let's dive into this because this number is just staggering. 88%. According to a recent study by systems architect Dan Mercede, 88% of real, public LLM schemas break on at least one major provider. And we aren't talking about schemas written by absolute beginners either. We're talking about schemas pulled directly from popular industry-standard frameworks like LangChain, Instructor, and official model context protocol servers. So why on earth are the tools we rely on generating schemas that fail 88% of the time?
Well, when we look across the major players, there's a massive discrepancy in rejection rates. OpenAI is rejecting a whopping 88% of these schemas, Cohere knocks back about 26%, and Anthropic sits at 12%. And then Gemini is over there with 0% hard errors, though, to be fair, it does generate a ton of warnings. But the big takeaway here, a schema isn't just universally valid or invalid. It's only valid for a specific provider. What works flawlessly for one language model might trigger an absolute meltdown on another.
So here's our roadmap for today. First, we'll unpack the 88% schema failure. Second, we'll look at the additional properties trap. Third, we'll demystify OpenAI's strict mode. Fourth, we'll explore clashing provider constraints. And finally, we'll talk about catching these errors in CI.
All right, let's kick things off with Section 1, the 88% schema failure, and the corpus behind it.
To really understand this massive failure rate, Dan Mercede set up a small linting tool and pointed it at 50 real production-grade schemas. This wasn't junk data, folks. These included 15 from official OpenAI and Anthropic cookbooks, 17 from popular agent frameworks, and 18 from official MCP servers. The results, honestly, they were shocking. Out of 50 production-ready schemas, exactly 3 passed completely clean across OpenAI, Anthropic, Gemini, Mistral, and Cohere. Just 3. It proves that the portability story for LLM schemas is basically broken right now. Again, valid for one simply does not mean valid for all.
Which leads us perfectly into Section 2, the additional properties trap.
Now, what's really interesting here is our primary suspect in all of this. It's a single, super easily overlooked JSON schema constraint, additional properties set to false. All this does is dictate that absolutely no keys other than the ones you explicitly defined are allowed in your JSON object. Basically, it locks the schema down tight. But here's the catch, and it's a big one. Standard schema generation tools, like Python's Pydantic, for example, don't emit this field by default. And because it's missing, language models that demand strict adherence just reject the schema entirely. Almost nobody sets this by hand, yet it's the #1 cause of failures.
In fact, in that 50 schema corpus we just talked about, the missing additional properties field alone accounted for 134 separate flags. Let that sink in. That is more than every other keyword violation combined. That's right, a single missing Boolean value is responsible for the vast majority of your schema headaches. It's literally just a tiny invisible string of text quietly taking down your entire application.
Let's move on to Section 3, OpenAI's strict mode demystified.
OpenAI has the firmest and most heavily documented constraint surface out there, which is exactly why it rejects 88% of standard schemas. So the crucial point is how you mechanically fix a standard schema to satisfy this strict structured outputs mode. It actually requires 3 specific steps. First, every single object must explicitly set additional properties to false. Second, every property must be listed in the required array. If you want a field to be optional, you can't just leave it out of the required list anymore. You have to put it in the required list but make its type nullable, like an array of string and null. And third, you have to completely drop any default values. Do those 3 things, and your schema will finally pass OpenAI's strict mode.
But this begs a massive question, right? Why is this trap entirely invisible until you actually hit production? Well, it all comes down to the dreaded, completely opaque API 400 error. When a provider rejects your schema, they don't give you a nice, helpful error message detailing exactly which constraint failed at which nested path. Oh, no way! They just return a generic 400 error saying invalid schema. And this forces developers into a state of sheer panic, manually bisecting their code at 2 a.m.,
desperately trying to figure out that a missing additional properties flag 3 levels deep in a nested object is what took the whole system offline.
Welcome to Section 4, Clashing Provider Constraints.
And just when you think you've solved it, we hit a major plot twist, because this is where the nightmare actually begins. Let's say you built a schema and painfully tightened it up for OpenAI. You added additional properties false, and maybe you added some helpful validation keywords, things like format, min length, or pattern, just to ensure the AI gives you good data. And OpenAI accepts that perfectly fine. Well, if you take that exact same schema and send it to Anthropic's tool, Schemas, they will violently reject it. Anthropic outright rejects those specific validation keywords in that context. So a schema perfectly tuned for OpenAI directly trips Anthropic's constraint surface. It's wild.
And this brilliantly illustrates a much bigger point. Shipping to multiple providers isn't about finding one universally correct schema. It is about satisfying a complex intersection of clashing rules. Take Cohere, for instance. They mandate that you have at least one required field per object. Gemini gets very nervous and throws warnings if you have a self-referential recursion or if you use the any-of keyword, which, by the way, happens all the time if a pedantic model references itself. Meanwhile, Mistral's documentation heavily implies they want OpenAI-like strictness with additional properties false set everywhere. You aren't just writing JSON anymore. You are literally threading a needle through 5 completely different sets of rules.
Which brings us to our final section. Section 5, Catching Errors in CI.
So how do we actually stop this madness? The definitive way to lock away these silent production killers is to use static checks during your build phase. Tools like SchemaFit allow you to encode these bizarre provider constraints as versioned rule packs. Basically, you run a static check that evaluates the exact JSON pointer paths of your schemas against the actual provider rules you use. This means if you miss an additional properties flag, or if you accidentally include a min-length keyword that Anthropic hates, the linter catches it. It fails the pull request in continuous integration. It fails the build before it ever merges, let alone reaches production. And honestly, the best part? These are static checks. They require 0 API keys, 0 model calls, and absolutely $0 spent on tokens just to verify your schemas.
Which brings us to this powerful concluding thought from Dan Mercede. He says, treat provider schema constraints as a CI concern, the way you treat types or lint. The days of treating LLM schemas as loosely typed suggestions are completely over. The constraint services are documented, sure, but they're scattered and they're opaque. So I'm going to leave you with this question. Are you going to keep playing guessing games with opaque 400 errors at 2 a.m.? Or are you ready to lock down your schemas in CI and finally take control of your structured outputs? Think about it. Thanks for joining me on this explainer, and I'll catch you next time.